Okay, hello. Welcome to Demystifying gRPC, a dive into the mysterious engine behind Instrument Studio measurement plugins. My name is Chris Delpire. I'm a software developer at NI, and I've been working with Instrument Studio measurement plugins for a while, so I'm excited to talk to you about that today. So I'm going to start out by talking about gRPC, giving a bit of a history of it and what it does, what it's good for. This is a technology that's typically used in the web and cloud space, but we've made really good use of it at NI. So I'm going to be doing a bit of comparing to other web technologies like REST, so you can see kind of the benefits of gRPC. And then I'll go over some of the different areas where we've been able to take advantage of gRPC at NI. So we have a lot of products that are enabled by gRPC. And during that time, I'll have Chad Erickson come up to give a little anecdote. And then finally, we'll end by talking about Instrument Studio measurement plugins and how that was built using gRPC and all the cool things that gRPC enabled for us. So gRPC was created by Google. It was released in 2016 with its 1.0 release actually in 2017. And this was a tool that was developed to replace an internal tool they had called Stubby. And so this solved a performance issue they had with server-to-server communication. So as you can imagine, Google has a huge amount of backend services and they need to talk to each other. And so they invented gRPC to be able to do this in a performant way. So for those of you who don't know, RPC stands for Remote Procedure Call. And this is basically a way for a program on one computer to talk to a program on another computer. You can also talk to programs on the same computer over localhost, and that's how we often use it. So does anybody know what the G stands for in gRPC? Any guesses? Google? So that's what I thought too, but it turns out that the G is different in every release of gRPC. So the 1.0 release, the G stood for gRPC, but it's changed every release since, and I believe 1.6.2 is the latest, so it currently stands for Guardian. So gRPC is an open source project. It's up on GitHub. It's under the Apache 2.0 license, which is a free and very permissive license, so anyone could use it for basically any purpose. And one of the big things it takes advantage of is HTTP 2. So this is a more performant version of HTTP where you have things like a binary format layer where you can serialize things with binary. And it has a lot of other advantages. It's using multiplexing to be more performant. gRPC supports SSL and TLS, so you can actually encrypt your data with certificates to make sure that your data isn't being sniffed when it's sent across the wire. And then perhaps the biggest benefit of gRPC is that it's supported in a huge number of programming languages. So kind of behind this green bar, I have several languages that support it, and LabVIEW is included in that list. So why is it so performant? Google invented a technology called protocol buffers. And basically what happens is you can serialize your data to binary. Typically in the web world, prior to this, you would use text encoding to send messages across the wire, and binary serialization is much more performant. In addition to being able to make server-to-server calls, you can do streaming. So you can do server-to-client streaming, and then you can do bidirectional streaming. So instead of just sending one message, you can send a whole stream of messages. So this is another reason that we use it. It allows us to be able to, in a performant way, send a whole bunch of data across the wire in smaller packets. Another kind of core principle of gRPC is that it follows what we call a contract-first design. So you start with the contract. You define the interface that your service is going to provide in gRPC, and then anybody who wants to use that service needs to fulfill that contract. So as I mentioned, I'm going to compare it to REST a little bit. REST is a technology that's often used when a browser is talking to a backend service. So you might have heard of HTTP GET and HTTP POST. And this is using text encoding. When you send a message to a backend server, that server might want to talk to other services that you have in the cloud. So for example, if you have a storefront, you might have a service that handles the user's account information. You might have a service that handles the items the user has put into their cart. And then you might have a service for ensuring that the inventory still has those items in stock. And so a lot of times behind your REST APIs, there's a whole bunch of different calls that need to be made to different services. And gRPC was invented to handle just that. And it does it in a very performant way, and it follows this kind of contract first approach. So you know, I can talk to this service, it's the version I expect, and I can expect to get the information out of it that I want. So as I mentioned, REST uses HTTP1 and text encoding. Basically, you're sending blobs of JSON across the wire, and as you can imagine, this isn't very performant. With HTTP2 and gRPC, we can do binary encoding. So in this case, the age field that we had over REST, it would be sent as a string, but now we can actually pack it as an integer. And so this is much more efficient. So to kind of recap, REST is suited for the web browser. It uses JSON serialization. It's basically ubiquitous in most of the websites and web applications you're using. Very simple and stateless. But gRPC provides this very powerful server-to-server communication, efficiently sending data with binary serialization. You get this streaming support that's really nice. And because it's a contract-first approach, you can strongly type things and write things in a language-agnostic way. There's a caveat. You actually can use gRPC in the web browser. There exists a project called gRPC Web, but it's limited. You can't do client-side or bidirectional streaming with it. And additionally, if you want to support REST APIs alongside your gRPC services, there's something called gRPC JSON transcoding that allows you to expose your gRPC services as REST APIs. And different languages, I think, have different levels of support for that. There are lots of alternatives to gRPC and REST, different web protocols that you can use, things like Thrift and GraphQL. GraphQL being made by Meta, and is a very popular way of efficiently fetching data. It's kind of more of a direct REST replacement. You have just regular WebSockets and then messaging or server to client event systems like RabbitMQ and Kafka. So diving a little deeper into gRPC, everything starts with a protobuf or protocol buffer. So here you can see we have a greeter service that is being defined. You can kind of think of this like a class you would have in a programming language. And in that service, you have RPCs, or your remote procedure calls. So in this case, we have an RPC called say hello. And with each of those RPCs, you're going to specify a request and a response. And these can be either a single request and single response, or if you want to support streaming, you can put the stream keyword in stream requests or stream responses. And so these requests and responses are what we call messages. And messages have a name and then a list of fields. And this is the actual data that exists within your message. So in this case, we have a hello request with a string name. And then we expect to get a hello reply with some message back. So fields are numbered starting at 1 and going up from there. And the reason they're numbered is in order to support this binary serialization. Because we're just getting a packet of bits back, we need to know what bits represent what fields in our message. And so by numbering them, we know what should be where. You can mark fields as optional. Technically, all the fields are optional. You don't have to set them. But if you use the optional keyword, in certain cases, you can get some optimization by skipping serializing those fields. There's the repeated keyword. This is how you get arrays or lists in gRPC. So you could have a repeated string, and this would be a list of strings in your message. And then there's this concept of one of that allows a field in a message to be one of a list of types. So you could have a field that is either one of string or one of byte. And it can be one of those two options. So gRPC supports all the typical data types you would expect, things like doubles and floats, integers of different sizes, as well as unsigned integers. You get Booleans, strings, and bytes as well. You can specify other message types as fields in your message. So you can have nested messages, which is great. It supports enumerations, so you can define enums and have them be fields in your messages. And then there are maps. You can think of this like a dictionary. And then there's the any keyword that allows you to specify anything in a message. And this is really powerful. We actually use this a lot with our Instrument Studio measurement plugins. Okay, so now you have a protobuf file. What do you do next? So you're going to take advantage of this thing, the Protalk compiler, to spit out what we call gRPC stubs. So you'll have a gRPC server stub. And this is kind of like a little blank canvas for you to implement your gRPC service. And then you'll have the gRPC client stub, which allows you to call into that service. So you'll create a channel, create the client stub, and then make calls to your gRPC service. Now, the nice thing is that because gRPC is supported among a huge number of languages, a lot of these languages have the Protalk compiler or some equivalent built into their tooling. So you don't have to do this manually yourself. If you're using .NET, you're going to pull in some NuGet packages that will have that for you, and MS Build and .NET Run will get that all compiled for you. Same thing if you're in Python, you're going to be using something like PyPy to pull down the packages you need to set up gRPC. So when you make a call, this is kind of the picture of what it looks like. The client makes the call. The message gets packed and serialized to binary, where it will get sent over the wire through HTTP2. The server will get that message and unpack it, deserializing that binary. And then the server stub, your server call implementation, is called. So you can do whatever you want with that data. And from there, you send your reply. This is also a message. It will get packed to binary, sent over the wire, and unpacked by the client, where it can then be used. All right, so you only need two things to call gRPC service. You need a protobuf file or some API that's already built a client from that protobuf file. And then you need an IP address and a port to talk to. So here's a little bit of Python code. Hopefully that's legible for you in the back, but basically, we're just creating an insecure channel. So like I said, gRPC supports TLS and SSL, but you don't have to use it. You can just talk over HTTP rather than HTTPS. So in this case, because we're on localhost, we're not worried about encrypting our messages. On port 5001, and so we create our greeter stub client with that channel. We create the hello request, and the name here is just you. And then we can call say hello. And so that'll get sent across the wire to our gRPC service, where we will get back our response message. And from there, we're printing the message to the screen. And then in this case, we also have a say hello again RPC, and that's being called afterwards. So I have a little video demo of me setting this up in .NET. The code might be a little hard to read on the screen, but at the end of each little section, I kind of blow it up, so hopefully it'll be more legible. But I have 3 projects set up here. I have a class library where I'm going to generate my stubs, and then that's being referenced by an ASP.NET Core server where I'm going to host the gRPC service. And I have a greeter client. This is a little exe where we're just going to print the response when we call the service. And so this is making use of that same, let's see if I can get this playing. There we go. So this is making use of that same protobuf file that we saw in an earlier slide. We just have an RPC called say hello that expects a request with some name, and it will return a message. So the first thing I'm doing is adding some NuGet packages to my greeter stubs project. And this will pull down everything I need in order to generate my server and client stubs. So there are 3 packages for .NET. You need gRPC tools, gRPC net client, and google.protobuf. And once those are installed, you simply build the project and those will get built. So now I'm actually creating the service class in my ASP.NET Core project. So I'm going to create a greeter service class. And this is going to extend that stub that was generated in my greeter stub project. So it's called greeter.greeterBase. And it has a method called sayHello, which I'll override. And I'll basically just take the request from the hello request and create a hello reply with a message that says hello and then the name that was sent to me. So you can see it's very simple to set up a server in this case. Of course, it's not doing a lot, but just getting it set up is quick and easy. So now I actually need to add a project to my greeter service. There's a gRPC.ASP.NET Core. And this makes it easy for us to map our service to endpoints in the gRPC service. So when I spin up the gRPC service, it'll have a port that it's listening for gRPC messages on. So you can see here I'm mapping the greeter service to my application. And if you're familiar with ASP.NET, this is very kind of natural .NET code that gets written. So this is really all you need to set up a service in .NET. It's going to be similarly easy in a lot of different programming languages. We'll show a LabVIEW example here in a little bit. And finally, I have to tell ASP.NET Core to use HTTP2 because gRPC runs over HTTP2. All right, so now I'm in the client project. I'm going to do a console.read key so that it won't run right away. I can press a button to get it to actually run. And so the first thing I'll do, just like in the little Python snippet, is create a channel. But you'll notice I don't actually know the port and IP address right now, so I'll get that in a minute. From there, I can create the client, the greeter client. This is code that was generated in our greeter stubs project. I can pass the channel to that client. And then I'll call my sayHello message, or the sayHello RPC. So I'm passing in a new hello request. I'm setting the name to Chris because that's my name. And then I'm going to do another console.read key and I'll print the message out to the screen. Okay, so now I'm running the greeter service. This is going to give us a little console that will tell us the ports that these endpoints are running on. So it's actually running both on a HTTPS and HTTP. So I'm just going to use the insecure port, and I'll paste that into my console application. So now I know who to talk to. And here you can see the final code. So the stuff at the top and the bottom is not really important, but the 3 lines in the middle is how you create a channel, set up your client, and make the call. And so here I have the service on the left, my console app on the right, and when I hit enter, it says, hello, Chris. And that's how quick and easy it is to set up a gRPC service and gRPC client in .NET and have them talk to each other. Of course, in the real world, your service is probably going to do a lot more than just turn around and say hello, but just getting set up is a nice experience. Cool. So this builds a really awesome world for us where the implementation of our services is decoupled from the implementation of our clients. In the example you saw, I was using .NET to call .NET, but I didn't have to do that. The code that you saw before, the Python code, would have worked just fine and been able to talk to my gRPC service as long as the client and the service are both fulfilling that contract. And so your options are unlimited. You can have a C# client or a LabVIEW client talk to a C++ server. You can have a service in Python that you can talk to in JavaScript, whatever you want. So that's kind of the power of gRPC. And from there, I'm going to talk about the different places where we've been able to take advantage of that. So typically, this is done in the cloud and web space, but we've actually found a lot of uses for gRPC in application software and for use with a lot of our customers. So the first project we have is gRPC LabVIEW, and this is the LabVIEW support for gRPC. So this is an open source repo up on GitHub that you could check out. And this allows you to create gRPC services and create gRPC clients in LabVIEW. So here's an example of what a gRPC server would look like in LabVIEW. This is that say hello again RPC that we saw before. And basically we have a VI to get the request. We can do some operations on the request. So in this case, just like I said, hello, Chris, we're going to say hello again, Chris. And then we pack that up into our response and send that back to the client. Similarly, the client service is very simple. So we have a panel where we can put our port and IP address. Who do we want to talk to? We have some controls for being able to set the data. In this case, it's John, not Chris. And then the VIs you see, we're actually calling both say hello and say hello again. So you create the channel, create the client, call, make the say hello and say hello again call, and then when you're done, you need to clean up your client. The next thing we have is gRPC device, and this is a gRPC server as well as accompanying client APIs that allow you to call our instrumentation remotely. This is also up on GitHub, open sourced and MIT licensed. And this might be hard to see, but pretty much every single one of our drivers is supported, particularly on Windows. We also have support for a number of them on Linux and Linux RT. And this is really cool because you can actually call your instrumentation on a PXI chassis from a remote PC. And this allows you to do a lot of different things. For example, you might have a test sequence where you're going to acquire some data and then run some analysis on that data. And once that's done, you can then acquire more data and do more analysis. And it's going to take some period of time. But if your test sequence is split across multiple machines, you can actually start pipelining these operations. So now your PXI controller can acquire some data. And then yes, there's going to be some latency sending that data to the remote machine. But once it's sent, your chassis is free to acquire more data while the remote PC is doing its analytics. So even though there's a little bit of some delay in there sending data across the wire, you're actually going to save time overall because you can kind of do these operations in parallel. And so now I'm going to pass it over to Chad, who's going to give a little anecdote.
Thanks, Chris. Chris did a great job already explaining what gRPC is, how it works. My job today, I won 5 minutes just to give you a little bit more color to why to use gRPC. I'm a customer facing. My name is Chad Erickson. I'm a California FAE, the Field Applications Engineer. Work with a number of people on the West Coast, and customers have come to me on the West Coast in particular to ask, how can I continue to use NI's amazing hardware products with a little bit different software and use case architecture? So I wrote a story. It starts in 2019, so quite a few years ago. Still stays true today. In 2019, customer came to me, gave me a few challenging requirements. Their main goal was, is there a better way to do system integration? We were starting to think about more domain-specific, using processors in particular for certain priorities, using other processes for others, dividing up workloads, doing distributed nodes. So if you're doing anything like that, you probably have common use cases, or maybe you're one of these customers. They were struggling a bit with remotability and hardware support. They've always loved NI. They used PXI, Compact Rio, LabVIEW, and TestStan on Windows for a long time. They were successful. And they started moving to other platforms for the benefits of those platforms. Those platforms includes Mac or Linux for the purpose of orchestration and for the purpose of peripheral activity. In particular, this customer wanted a non-Windows compute, potentially because of security or registry reasons, blue screens. They wanted the ability to use that platform for sequencing, for data collection, for processing, for distribution back to their databases. But they didn't want to give up anything. And so they said, Chad, that's my core request, but here's a few others. And so I started jotting these down as requirements. They needed an industry standard way to communicate to our products. They didn't want a one-off. They wanted, open source. minimal cost, availability. So they wanted to de-risk future obsolescence. Of course, they had the original things you usually get from NI. They wanted scalability, flexibility, supportability in the future. My job as an FAE, by the way, if you ever talk to any NI FAE, is to ensure success for customers that adopt NI products. That's our only job. If any FAE tells you anything different, they're kidding you. That's all we're here for. We're here to look out for your success, for maintenance and supportability. Number 4, they wanted easy to use, easy to get started. If I failed to provide something that was easy to get started for a number of new users, they weren't necessarily interested. And then the last one. By the way, by number 4, I still had a number of options. I was ready to finish, listen down these requirements and jump and say, hey, I got some great options for you. But number 5 got me. Number 5 was I need high speed. I need low latency and or like production test throughput. Guess what I did? Oh, my shoulder sagged. And I said, well, maybe we should just talk options and trade-offs then, because what you just asked for, that's the trifecta unicorn. You want low cost, you want high quality, you want high speed. I was like, I'm gonna do my best. Let's see what I can do for you. So what do you think I was gonna recommend? Anybody? Like no? From the first 4 requirements? Obviously it's promotability, talking from one place to another. What do we use? Industry standard, it's been around for a while. Probably a few, right? I see some of you mouthing it. Our customers use Skippy. They use interfaces that enable you just to talk. They use REST. You mentioned it, Chris, in your beginning. Just ways to transfer data from one place to another that most people know and can succeed with. However, is that high performance? Depends on what you're doing. For production test, you're gonna get a little bit of latency there and delay. So we talked about the benefits of Skippy. It's simplicity, it's industry standard. We talked about HTTP 1.1, which is the REST APIs. Talked about some other NI options like Skippy RF that we had at the time. RPyC, if you ever use Python remote procedure calls. It's kind of like remote Python calls. They weren't as performant as the customer needed. We then talked about the higher performant options. So these are things that NI's had for a long time. We still do. These are Ivy drivers. They're compiled in usually a programming language like LabVIEW or C++. They're enabling you to communicate highly effectively with minimal latency and delay. We also have our native device drivers. If you're on a supported platform, you have native drivers. NI-DACMX on Windows is a native supported driver. It works very performant. Of course, these have the issues of not being cross-platform. Can't be used across multiple programming languages. We then started diving into these newer RPC things that were being developed or around for just a little bit of time. We saw JSON RPC, which is a great one, taking text as a JSON file and being able to push it onto the Ethernet layer. And then we found gRPC. And gRPC had this small little note at the bottom that this is a performant capability that enables you to connect one system to another, client to server, server to client. By the way, I just want to ask, how many of you have heard of gRPC before today or have used it before today? Good. So you guys have already used it, so you already know. Maybe not for this particular use case, for connecting to a piece of hardware or a functionality on a distributed node, but maybe just to communicate in the cloud or doing some kind of computational power. But that's what I stumbled on at that point in time. And that's my customer anecdote. I explained to the customer at that time, gRPC uses binary message formatting, allows you to support streaming, has built-in support for load balancing, authentication, encryption, things the customer needed for performance, for security. We went through all their requirements. gRPC was platform independent, supports a wide number of programming languages and environments. It's industry standard, it has protofiles that are defined, says everything that your messages can do, all the parameters that are defined within those methods, and the protocol buffers underneath that took your message that you were about to send, and it makes it binary, and it serializes it so it can be transferred in a very efficient manner, an optimized manner. It's optimized for performance. So no longer are you working on a slow handshake. Now you're streaming data at a very fast rate. I was looking at published benchmarks just recently, and they have somewhere around 8,000 or so RPC methods a second for a 32-byte message. So if you think about that, that's roughly 12 and a half microseconds per RPC call. That's good. That's what the customer wanted at the time. Absolutely scalable. You can reuse these APIs and you can build on top of them. Flexible, you can create multiple distributed nodes, PXI in one, Compact Rio in another, multiple servers on each. Clients can connect to one or more. Sustainable, supportable. There's more tools out there now than there were in 2019. We have ways that you can do codeless clients with gRPC, where you can take your proto file, which defines all those messages, and you import it into these codeless clients, and suddenly you can automatically just run these messages. You just need to give it the IP address you want to talk to, the port you want to talk to, credentials if needed. You can push these run commands and you'll get the response. Great way to do diagnostics. Great way to make sure that your system's working as intended. And then there's things like Wireshark that we've always had. gRPC is based on TCP, so you can Wireshark it. And there's now add-ons with Wireshark called gRPC that enable you to see what the binary transfer is. So diagnostics is definitely capable here. I think that's pretty much it. Talked to them about gRPC device that NI developed. We put our drivers out there. We exposed all of our driver C API via gRPC so customers could start with our C help and develop a communication protocol that worked for them in a small amount of time. Get up and running quickly. So I'm happy to say, even at that time, the customer was super excited to get started. And gRPC has been successful since. We've deployed a successful number of production test systems and now a fair number of validation systems, all leveraging gRPC. And I want to let you guys know, the slide says it yourself, but this may be, you're exploring it and you want to talk to somebody about maybe how things were implemented in the past for their use case. Maybe you've already implemented it and just have questions on maybe a challenge you're trying to overcome. Whatever the question might be, I'm willing to take questions after the session, and I'm very much willing to be brought in with potentially your salesperson or your FAE and get you to where you need to go. So I thank you for your time. I'm going to hand it back over to Chris.
All right, so that's awesome. Real world use case of customers taking advantage of gRPC and getting huge benefit from it. So thank you so much for that. So continuing on with the different places we use gRPC at NI, we also have the gRPC test stand API that's up on GitHub. And this is kind of an early access project that allows you to execute test stand sequences remotely and control test stands remotely. So if you're interested in that, it's a really great project. In Instrument Studio, we have RF panels, and these can communicate over the wire remotely to talk to your RF instruments. This morning, you saw the exciting announcement of the Instrument Studio Professional Edition. And as a part of this, we have a sequencer that's built into Instrument Studio, and this is taking advantage of services as well. And so finally, that brings us to Instrument Studio measurement plugins. So what are Instrument Studio measurement plugins? Well, this is a new platform that we have in Instrument Studio Pro that allows you to write measurement IP, and it will exist as a gRPC service and can be called from Instrument Studio. You can call it from test stand, from wherever you want. So we're taking advantage of gRPC to make a very flexible plugin model for Instrument Studio. What's kind of the problems with the traditional plugin model that we see in a lot of applications today? The first issue is that when you write your application, you've picked some programming language like C#, and your plugins are kind of bound by that. If you want your customers to extend your application, they're either going to need to write their plugins in the same programming language, or you're going to have to provide some sort of interface or some interop to support whatever programming language they want to write their plugins in. And then what happens if one of these plugins has a fatal error? You have to be careful managing these plugins and ensuring that if one of them has some sort of fatal problem, it doesn't bring your entire application down. If two of these plugins share a dependency, but they are referencing different versions of that dependency, then you could be in a lot of trouble. If you try to load both of those plugins, one of them might fail to load because of this dependency issue. And so you have to worry about dependency and plugin isolation. And finally, the debugging experience for plugins is not very nice. You're kind of stuck in the stack of the application that you're writing your plugin for. And so it'd be really nice if your plugin can just kind of exist independently and be debugged independently. Next up in test stand, if you want to reuse your plugin in test stand and use a step type that's built into test stand, you might be limited to one of these programming languages. And even worse than that, if you want to use plugins from other vendors, they better be in the same programming language too, because you can't easily share instrument sessions between different programming languages in test stand. And so that can be something that's a bit tricky and something that gRPC device actually helps solve. So in the Instrument Studio measurement plugin world, your measurement is going to exist as a gRPC service. You can think of it kind of like this black box that everyone knows how to talk to because it's following this contract first approach. We have a measurement service gRPC proto file that your service is expected to fulfill that contract. And because it does, we can call it from test stand, we can call it from Instrument Studio, and you can call it from any other programming language for that matter. So I'm going to show a quick demo. You got to see it this morning, but this demo is going to show it again and then also show how easy it is to debug these measurements. So I have a LabVIEW project here with a scope acquire waveform measurement. Inside of this project, I have a run service VI that's going to spin up the gRPC service for me. From there, I can open up Instrument Studio separately. I didn't need to have Instrument Studio opened first. And Instrument Studio will load my acquire waveform measurement. So you can see I was able to run it and get some data back. But now let's say I want to debug this measurement. Well, going back to LabVIEW, I can open up the VI that has all my logic. I can set a breakpoint wherever I want. And I'll do that here. And then when I go back to Instrument Studio and run the measurement, LabVIEW will just break at my breakpoint. And now I can set probes and do any kind of debugging tasks that I want to do. So you can see it's very easy to set this up. You don't have to do anything complicated to be debugging Instrument Studio measurement plugins. That's not to say that there aren't challenges that are introduced by going to a microservice architecture and using gRPC. One thing that can be a bit complicated is managing state. So now you have this ability to share instrument sessions with gRPC device, but you need to make sure that services aren't stepping on each other's toes. So you need some way to register your sessions and then reserve them to say, hey, I'm using this, no one else can use it. In addition to that, you might be someone who's using a pin map to talk to your hardware. And so if you want to use your measurement in Instrument Studio and then run it again in test stand, both of those applications are going to need to know about your pin map. And finally, how do you discover services, get the IP and port address that you need in order to be able to call them? So Instrument Studio measurement plugins come with a bunch of utility services that all kind of run behind the scenes to help you solve these problems. We have the discovery service that helps you find what measurement services are installed on the machine and what their IP and port is. We have a monitoring service that helps synchronize data between Instrument Studio and test stand. So you can be running measurements in test stand and seeing the results in Instrument Studio at the same time. And during the keynote this morning, I believe you saw an example of that. And then finally, we have a pin map service, session management service, IO discovery service. These help solve that state problem I mentioned before. So with the pin map service, you register your pin map and say, this is the pin map I'm using. And test stand and Instrument Studio can then reference the same pin map. With the session management service, you can say, hey, I'm using this session, and that'll prevent other measurements from using it while you're using it if you want to be able to run things in parallel. Okay, so how do you create a measurement? Well, you're going to need a gRPC service. From there, you need to implement this contract that we talked about. So you'll need our measurement service proto file. We then have this file called a service configuration file, and this is a small piece of JSON that just tells us things like what is the name of your measurement, how do we start your measurement up if you want to register it statically, what interfaces does your measurement provide, what contract does it fulfill. And then you'll need to create some user interface if you want to be able to use that measurement in Instrument Studio. And finally, once all that's set up, you can register with our discovery service and you'll be available to all our applications. So we have yet another GitHub repo, the NI APIs repo. This is where our public proto files live, and it's where you can get the measurement service proto file to create a measurement. And so this is what that looks like. It's just 2 RPCs. We have a get metadata RPC, and this is kind of a way of making these measurements generic. So get metadata will tell us what are the inputs to your measurement, what are the outputs. And from there, you can call the measure RPC. And this is the real meat and potatoes where the measurement is being done. So your measurement service will spin up and register itself with the discovery service. Instrument Studio will then ask, hey, what measurements are available on the machine? And then you can select your measurement and it will be resolved. We'll get the IP address and port for that measurement. And then Instrument Studio can talk to your measurement directly. Okay, so you might be thinking that sounds like a lot of work. Well, that's the use case that supports any programming language you want. But if you're using Python or LabVIEW, we actually have first-class support for those languages. So we've taken a code-first approach where we've created APIs that abstract gRPC away, and you can just write native Python code or native LabVIEW code and very easily set up a measurement. We'll do things like handling the discovery service registration. You have to provide us the service configuration, but from there, we'll register your service. We'll create the channels that you need in order to call the session management APIs, the PinMap APIs, whatever APIs you need. We have API wrappers for those. So the Python support is up on GitHub, open sourced and MIT licensed, and you can actually get all the dependencies you need from PyPy. And similarly, we have the LabVIEW support up on GitHub, and these dependencies you can get from VI Package Manager. So here's that blob of JSON I was talking about before, the service configuration file. You specify the display name of your measurement. This is what customers are going to see when your measurement shows up in Instrument Studio or Test Stand. Then you give us a service class, and this is kind of a unique name for your measurement, so we know exactly who we're talking to. And then the provided interfaces is that contract that your measurement fulfills. So we have V1 and V2 measurement services. You should just go ahead and go straight to V2. It supports streaming responses back. I mentioned that you can set up measurements to be installed statically with the discovery service. So there's kind of 2 models that we support. The first is a runtime registration. So that's what you saw in the LabVIEW demo, where I just simply started the service. The service registered itself with the discovery service, and from there I was able to make calls to it. But once you're done kind of testing, debugging, your measurements ready to be shipped, you're going to want to install those on machines and not have to go and run them manually. So you can do what we call static registration, which is installing your measurement to a known location. And part of the service config is specifying a path to tell the discovery service, how do we spin up your measurement? So in this case, we're a Python measurement, so we can just run a batch file to run the Python commands we need to spin up the measurement. If you're in LabVIEW, you can build an executable and put the path to that executable here, and so our discovery service will know how to spin it up. And finally, we have some annotations, and this will help your customers find your measurement in Instrument Studio. You can do things like filter based on description or different kind of tags. So I'm going to start stepping through that DMM measurement in Python. So in this case, we're using that service config to register with the discovery service. This is the bit of code that will run when your service runs to tell the discovery service, here's information about me, here's the UI that I use. So there's two options when you're building user interfaces for your measurements. You can use LabVIEW, and this allows you to build very rich and powerful user interfaces. But if you just need a very simple and quick user interface, we have a product called the Measurement UI Editor, and it allows you to drag and drop controls and bind them to your inputs and outputs. And so I'll show a picture of that later. From there, you just kind of write natural Python code. So we define a measure method. This is the method we expect to be called when Instrument Studio or Test Stand calls measure on our measurement. We need to use annotations to tell us what are the inputs and outputs for that configuration. So that is all these things at the top with the @ symbol. The inputs we call configuration and the outputs are outputs. For each of those, you give them a name. You tell us what data type you expect it to be. So in this case, we have an enum, a double, another double. And then you can define the default value for those things. So when somebody launches this in Instrument Studio and loads the UI for your measurement, the controls will get populated with the default values. And so from there, you just write the normal Python code you would expect, and you return the different outputs that you said that your measurement supports. And so this is what the actual measurement code would look like in this case. We are reserving a session with the pin name. So this is taking advantage of the session management service and the pin map service that I talked about before. So this is all built into our Python support. You don't have to make these calls manually. You just say, hey, I want to reserve the session for this pin. And we'll go out and talk to the pin map service and say, okay, what device are you connected to? Is that device created and registered? If not, we will create it and register it for you. And then we'll reserve that session. And so then you can say reservation.initialize DMM session and get a session back and then go through and do all the kind of normal DMM Python code that you would write if you were just talking to the Python API directly. So we're configuring some measurement digits, doing a read, and then returning information back. And so here's what that measurement UI editor looks like. You can see we have this left rail with several different control types that you can use. You can actually run your measurement directly in the measurement UI editor. So you can test it while you're building your user interface. And when you drag and drop these controls, we will show you what inputs and outputs are available for you to bind those controls to. And so this is a very quick and easy way to support building measurements. And then here it is in Instrument Studio. Looks exactly the same. And then in test stands, you'll drop a measurement step onto your test stand sequence. And at the bottom, there's a step settings panel that will be populated with all the inputs and outputs that you've defined for your measurement. And so from there, you can either just put values directly into the step panel, or you can bind them to test stand variables, run your measurement in sweeps and loops. And it'll also be possible to use these measurements in the Instrument Studio Pro sequencer that will be available in Q3. So that's kind of the quick overview of Instrument Studio measurement plugins. We've built this on gRPC and really been able to take advantage of gRPC to make writing measurements quick and easy, making it very easy to debug your measurements, and allowing you to reuse this measurement IP across our portfolio of applications. So you're not having to write different code to support it in Instrument Studio and to support it in Test Stand. If you want some more information about Instrument Studio Pro or about the Instrument Studio measurement plugins, there's some talks that I would recommend. I don't actually know if these times are right because I believe the times were changed, but today in the afternoon, we should have the Instrument Studio Pro, a low-code environment for manual and automated measurements. I'd strongly recommend that talk. It should be in room 17A. You can check out what's new in LabVIEW. And then we have Make Measurement Reuse Your New Superpower. And this will go into more information about Instrument Studio measurement plugins. And that is tomorrow at 2:45 in room 19B. And then tomorrow we also have a hands-on in Ballroom E that you can check out, the workflow from instrument bring up to test automation. And so that should have more information as well. And so from that, I think we're good on time for some questions, if anybody has questions.
This is just a general purpose gRPC question. So, you've talked about a lot of applications where you're talking from LabVIEW to something else, or through MeasurementLink. But if I just have a standard, like an RT system producing a bunch of data, and then I need to be able to stream that to a Windows system, do you have any benchmarks on how gRPC would compare to something like network streams or other platforms? I mean, is it a good choice if I just want to stream LabVIEW to LabVIEW over a network?
I think so. Chad might have some more hard data on that.
So we did that. I don't think I took benchmarks in regards versus network streams or other, like I'll say network variables, just basic use cases for RT to Windows communication. But gRPC does work for that. And we've done it internally with other products as well that were transmitting data from one processor to another. In particular, it works really nice from Linux real-time to Windows. And LabVIEW can both be the server and the client. gRPC LabVIEW was the very first thing that was shown. It's kind of like the custom creation that can do automated scripting, code gen within LabVIEW for the purpose of creating server code. And you can then create a client in the same way. So I'd recommend it. Give it a shot. I don't think you're going to run into too much difficulty.
And I believe technically there are some things over TCP that are even higher performance, but very difficult to get set up. And gRPC is performant, easy to use, supported across a bunch of languages. It's really the de facto choice. And that's why it's so popular in the web world. And it's a huge benefit to us as well. So.
Yeah, do you have the tools in the gRPC, I guess, multitude of GitHub repos? Do you have some of the tools to deal with proto-buffers that you guys have not incorporated? So maybe I develop a proto-buffer for streaming data potentially, or for dealing with any multitude of things, and I want to produce that proto-buffer within LabVIEW natively. Do those tools exist, or am I still not able to do that?
So for that, you'll need to use gRPC LabVIEW. You'll write your proto file, and then you'll pull those packages down. I think all those packages are on VI Package Manager. And in LabVIEW, you can tell it to generate a gRPC service based on that proto file, as well as a gRPC client. From there, if you want to use it with Instrument Studio measurement plugins, you can actually register that with the Discovery service. Now, we won't have anything that's looking for that contract or that interface, but you can at least have it available if you're writing other services that you want to discover that service that you created.
Sorry, follow-up question. Yeah. Sorry, a small follow-on question. I guess more fine-tuned than that. If I want to just generate proto-buffer data within LabVIEW, do the tools exist within the gRPC LabVIEW GitHub repo and the packages there? Not necessarily to publish them or to use them as part of a gRPC process, but just to purely make proto-buffers within LabVIEW for publishing in different ways, or for storing or dealing with in different instances.
I think
we might have an answer back here.
We got a guest speaker in the back.
Super expert has joined us.
You want to?
Yeah.
I mean, so yeah, for LabVIEW itself, we have inside of the gRPC the same packages. There are APIs to generically just read and write protobufs. So you can just use the same tooling to generate the message. So basically the cluster wrappers and things like that. And then there's APIs to pack and unpack a message. When you pack a message, you basically just get back the binary byte array of that data, and then you can unpack it again later. There's also tools in LabVIEW. If you don't know the actual structures of protobuf, you can walk it generically as well. So that should let you do anything you want to do within LabVIEW itself.
Yeah, I really appreciate you guys coming to my technical presentation, and I hope you enjoy NI Connect. Enjoy your week.